Welcome to this explainer. Today, we're dusting off a literal mathematical masterpiece, A.P. Kiselev's 1909 Elements of Differential and Integral Calculus. What we're actually looking at here is a modern English translation from 2026. It perfectly preserves the original math, byte for byte, but gives us this amazing, clear window into how early 20th century minds structured the entire world of mathematics. Our goal today? To totally demystify the core tenets of calculus, using Kiselev's incredibly elegant step-by-step logic. And hey, to avoid any math anxiety right out of the gate, here is our clear 5-step roadmap for bridging the gap between the finite and the infinite. The language of change, approaching the infinite, solving geometry with limits, discovering the number e, and finally, the unbroken curve. So let's start with a pretty provocative question. How can we possibly measure something that never ends, using entirely finite tools? I mean, we live in a finite physical world, right? But to truly understand curves and areas and continuous motion, we have to somehow find a way to trap and calculate infinity. This was the ultimate mathematical puzzle, and Kiselev's text provides an absolute masterclass in how to solve it. Okay, let's dive right into section 1, the language of change. Because, before you can calculate infinity, you really need to understand how things relate to one another. Kiselev defines a function simply as a quantity that changes when certain other quantities change, and he brilliantly grounds this super abstract concept with a real-world analogy right in his introduction. He points out that the duration of a pendulum swing is simply a function of its length. If you change the independent variable, the length of the string, the dependent variable, the time of the swing, changes right along with it in lockstep. It's this unbroken, completely predictable relationship. To keep all of this organized, Kiselev categorized these mathematical relationships neatly into distinct classes, basically establishing the rules of engagement for the rest of his book. He divides them into explicit functions, where an equation is already solved for your variable, and implicit ones, where it isn't. But more importantly, he separates the algebraic functions, which just use basic addition, subtraction, and roots, from the transcendental functions. Those are the ones that transcend simple algebra entirely, like trigonometry and logarithms. These distinct categories basically act as the playing field for everything that follows. Which brings us to section 2, Approaching the Infinite, where we explore the true superpower of calculus, limits. Before we can master limits, we have to wrap our heads around a very specific, kind of mind-bending concept, the infinitesimal. Kiselev defines this not just as some really small number, but as an active, shrinking variable. It's a number whose absolute value becomes, and crucially remains, less than any given positive number you could possibly think of. It is constantly tending towards zero, just slipping smaller and smaller, forever approaching nothingness without actually disappearing completely. And when you manage to capture exactly where that infinitesimal is heading, well, you've found its limit. Actually, here's a really fascinating historical nugget from the translator's preface about this. In the original 1909 Russian text, Kiselev used the abbreviation pred from the Russian word predel to denote a limit. This modern English edition maps that directly to the familiar lim notation that we all use today. It's just a great reminder of how mathematical language evolves across borders and centuries, even while the underlying logic stays exactly the same. Now, what's really cool is how we apply these tools in section 3, solving geometry with limits. Think about a perfect circle for a second. It's a perfectly smooth curve. If you only know how to measure straight lines, finding the exact perimeter of that circle seems mathematically impossible. But Kiselev uses this brilliant 3-part proof involving limits to solve it. Step 1, you draw polygons inside and outside the circle. Step 2, you double the number of their straight sides indefinitely. And step 3, you prove that as the sides shrink to infinitesimals, the difference between the inner and outer perimeters tends exactly to 0. This brilliantly illustrates the entire concept. You can see how the inner and outer polygons form a sort of jagged shell around the circle. But as you scale the number of those straight sides to infinity, the jagged lines literally approximate the continuous curve. The finite straight lines, when pushed to an infinite limit, actually become the circle. The perimeter of the polygon becomes the circumference. It's a stunning piece of logical bridging. And taking it a step further into 3 dimensions, Kiselev doesn't just stop at flat circles. He takes those exact same broken polygonal lines and rotates them around a central diameter. By calculating the surface area of the resulting rotating cones and pushing their side lengths to 0, he seamlessly proves the surface area and volume of a perfect sphere.
He takes the strict rules of straight, blocky 3D geometry and completely smooths them out using the limit of the infinitesimal.
This geometric mastery naturally sets us up for Section 4, discovering the number e and unpacking the natural base. In Section 24 of his text, Kiselev introduces an infinite series of fractions. It goes like this. You start with 1, then you add 1 over 1, then add 1 over 1 times 2, then 1 over 1 times 2 times 3, and so on. Because those denominators are getting absolutely massive, the fractions you're adding are rapidly getting smaller and smaller, basically approaching 0. By comparing this to a geometric progression, Kiselev rigorously proves that even if you keep adding these slices infinitely, forever, the total sum must continuously increase, but it will never, ever reach the number 3. So the crucial takeaway here is that this infinite addition locks in on one specific transcendental value. It is permanently trapped between 2 and 3. As the terms approach infinity, the sum settles exactly on the number e. Kiselev notes that taking just 11 terms of this series gives us the value accurate to 1/10 millionth, 2.7182818. This isn't just some random decimal, it's literally a fundamental constant of the universe. It governs everything from compound interest to radioactive decay. This number e is so vital that it forms the base of the entire natural logarithm system. And the translator notes something really cool about Kiselev's original formatting here. While today we usually use ln to denote the natural logarithm, Kiselev distinctively denoted it with a capital L, writing log to set the natural system completely apart from ordinary base 10 logarithms. I think it really highlights the reverence early mathematicians had for this natural system of growth.
All right, let's bring all this abstract math back to something we can visually picture in Section 5, the unbroken curve.
We've talked about functions and limits, sure, but how do they behave in motion? Well, Kiselev defines a continuous function with strict mathematical precision. Simply put, it means there are 0 gaps. It takes a definite real value, and this is key, an infinitesimal increment of the input argument causes only an infinitesimal increment of the output function. Basically, a tiny change in your x creates only a tiny, predictable change in your y. No surprises whatsoever. Kiselev mapped this beautifully on coordinate axes. You can see in this original hand-drawn graph how the sweeping, elegant line traverses the x and y axes. Because the function is continuous, individual plotted points blend perfectly into a single, unbroken curve. As Kiselev explains it, if you imagine x varying continuously, the locus of all those points forms a continuous line that visually represents the law of variation. It is literally the mathematics of smooth, predictable reality. But what happens when that rule breaks? What happens when a tiny change in your input doesn't result in a tiny change in your output? Kiselev points out that certain functions, as they progress smoothly, hit a specific value where they suddenly and violently rupture. Imagine a fractional function that drops instantly from positive infinity all the way down to 0. Kiselev dramatically and honestly kind of poetically calls this a discontinuity of continuity. The smooth, predictable line vanishes and a sudden, infinite jump occurs. Which leaves us with this final thought. If calculus is the underlying language we use to model reality, how might these 1909 theorems about sudden mathematical jumps, these discontinuities of continuity, explain the chaotic, unpredictable shifts we see in our modern 21st century world? Whether we're talking about sudden stock market crashes, the snapping of a stressed physical material, or massive tipping points in climate patterns, understanding exactly how the math breaks might just be the key to understanding how our world breaks. Definitely something to ponder as you look at the continuous curves in your own life.